Hello! In this video, I'd like to introduce you to model theory, the way that I was introduced to model theory, in terms of linear orderings. So what is model theory? Well, model theory concerns itself with the study of mathematical, specifically logical languages. So let's think about this from an analogous perspective. Suppose that you have a computer programming language. Because that computer programming language is bounded, what constitutes a valid program is very precisely defined by the specification of that programming language, and unambiguous. Each program has a precise behavior according to the specification. We can mathematically analyze programming languages to ask, what can we say? In other words, what sorts of functions can we implement in our programming language? And of course, hopefully the answer is that it's Turing complete, but not for every programming language. And we can also ask questions about how complicated it is to say these things, to write a program to do a particular task in this particular programming language. And analogously, mathematics, well, mathematics is unambiguous, but it isn't bounded. People are constantly adding to the mathematical lexicon every day. But if we focus on a bounded subset of mathematics, if we say we're only allowed to use this very precise set of mathematical symbols and constructions in our formulas, what are the things that we can say? What are the things that we can express in this very limited mathematical language? And how hard is it? How complicated? We can have various measures of the complexity of a particular formula, and we can ask, how complicated is it to say these particular things in these particular languages? So that's what model theory is all about. And the sort of languages that model theory primarily concerns itself with are first-order logics. So you've probably seen first-order logic before. It shows up everywhere throughout mathematics. It's specifically, you're allowed limited quantification. You have some sort of domain of quantification, and all quantifiers are quantifying over that particular domain of quantification. So this talk, I'm going to be focusing specifically on the first-order logic of linear orderings. So let's be really precise about what this language is. Specifically, we're allowed variables, and those variables are going to represent elements of our linear ordering, so numbers or points or whatever sorts of things we're putting together in our structure. We're allowed a comparison relation, less than or equal to, which we can then use to build less than, greater than, and less greater than or equal to. We have equality. We can talk about two variables representing the same element of the linear ordering. We have Boolean logic, so and or not, true, false, implies, things like that. And then, of course, we have quantifiers. We're allowed to quantify, we're allowed to say for all elements of the linear ordering, or there exists an element of the linear ordering. So, for example, we can say that for every x, x is less than or equal to x. Of course, it's equal. We can also say that for every x and for every y, if x is less than or equal to y and y is less than or equal to x, then x is actually equal to y, and so on and so forth. We can write out the axioms of what it means to be a linear ordering in this particular logical language. So these formulas are true for every linear ordering, but there's also formulas that are true for some linear orderings. So for instance, some linear orderings, and if you're not comfortable with linear orderings, you could just think of subsets of the real number line. You're missing out on some of the fun infinite things that you can do with linear orderings. They can get really infinite going inwards, they can get really infinite going outwards. You can't really do that with subsets of the real number line. There's limits to how infinite those things can get. But you're not really missing out on anything from a model theoretic perspective. So you don't need to worry about that. You can just think about subsets of the real number line. But let's talk about some of the things that we can say in first order logic. We can say that there's a smallest element, right? So there exists an x, that'll be our smallest element, such that for any y, y is greater than or equal to x. Of course, y could refer to the same point as x. So we have to allow the option that y is equal to x. We can kind of flip that around and say something like there's no largest element, so for every x there is a y which is strictly greater than x. So some linear orderings are what is called dense. Between every two elements there's another element, and in fact there's going to be infinitely many, but once you have that there's one, there's infinitely many. But not every linear ordering is dense. Some linear orderings have points that have what's called an immediate successor. In this case, we say that x has an immediate successor, y, if y is strictly greater than x and there isn't a z between y and x. So let me show you some examples of linear orderings, and I'll show you the notation that I'll be using to refer to these linear orderings. Suppose that we have a linear ordering with 5 points in it. It doesn't really matter what the 5 points are. They're all going to be isomorphic to each other. So we don't really care about what the names of these particular points are. So we can just have 5 arbitrary points. I'm just going to draw those as 5 points, and I'm going to refer to the 5-point linear ordering with just 5, and I'm going to do that for every finite number. Things really only get interesting when we start talking about infinite linear orderings, and kind of the simplest one, we can talk about omega, which is the linear ordering of the natural numbers. So it still has this kind of spacing. Every element has a successor to it, that there's nothing in between, but this one doesn't have a largest element. So we can also talk about the linear ordering of negative integers, and we call that omega star. The star is an operation on linear orderings that flips it around. So this is specifically, we take omega, we flip it around, and we get omega star, that linear ordering. We can also combine these two together to get zeta. Think zeta, think z, think the integers, right? This is the linear ordering of the integers. And actually, one of the fun things we can do is we can take these two pieces, we can take omega and omega star, and actually flip them around to produce what's my favorite linear ordering, which is omega plus omega star, which we can see here below. Plus is another linear ordering operation that just takes two linear orderings and kind of sticks them together, where everything in one linear ordering is declared to be less than everything in the other linear ordering. So what we get is a linear ordering that has endpoints, and it goes one by one, and it's infinite in the middle, and there's some really cool properties of this particular linear ordering. And finally, we have eta, which is the linear ordering corresponding to the rational numbers. I've drawn this a little bit strangely, but I really wanted to capture the idea that between any 2 points, there's another point, and there's no largest and smallest point. So this is how I've chosen to represent that. So how could we possibly analyze this first-order logic language? It seems like a really complicated language. There's lots of things going on. We have quantifiers, we have Boolean logic, we have less than or equal to. We can have lots of different things that are going on. We can combine these things in lots of different ways. How can we analyze what sorts of things, what sorts of properties we can describe in this language, and what sorts of properties we need something more powerful in order to be able to describe? How could we possibly start answering that sort of question? And the answer is through what are called Ehrenfeucht-Fraïssé games. This is, in my opinion, really the most accessible way of getting into model theory. They're really straightforward games, and you can use your intuition for playing games in order to analyze them. So an Ehrenfeucht-Fraïssé game, we have two linear orderings. We imagine possibly one drawn on top of another. And we have two players. Player 1 is called spoiler, and player 2 is called duplicator, and they have very asymmetric roles. Player 1, on their turn, picks a point in either of the two linear orderings, and they shouldn't pick a point that's already been picked before. And then duplicator should pick a point in the other linear ordering to match it to. And the rule is that duplicator can only match points in such a way that matched points in one linear ordering stay in the same order in the other linear ordering. And I'll show you what that looks like. Duplicator's goal is to last as long as possible, and spoiler's goal is to end the game as quickly as possible. So let's take a look at one of these games in action, and you can play along at home. Here we have two linear orderings. We have omega at the top and we have zeta at the bottom. And let's just see what happens, how the game plays. So spoiler is allowed to pick any of these points, any of the points on the screen on their turn. Let's say that spoiler plays here. Then duplicator on their turn is going to want to match this point down here with one of the points up at the top. So let's say duplicator matches it to this point here. And then let's say spoiler plays here. So duplicator then has to play one of these points on the left side of this point here. Duplicator cannot play at any of these points because that will cause the lines to cross, and that can't happen. So let's say that duplicator plays here. Now spoiler can play here, and there's no point in between these two for duplicator to play at. So duplicator has lost in 3 turns. So I'll let you think about what's the optimal strategy for spoiler. How fast can spoiler end the game? And how long can duplicator make the game go on for? So the intuition here is that spoiler wants to take advantage of the difference between the two linear orderings. And in this case, these linear orderings are pretty similar to each other, except that omega has a least element and zeta does not. So spoiler wants to take advantage of that. So on their first turn, they're actually going to want to play at the least element of omega. And then duplicator can match that to, it really doesn't matter which point duplicator picks, they're essentially all the same from a game theoretic perspective. So let's say duplicator picks here. And then spoiler can pick this point here, and duplicator has nothing to match it to. So duplicator can actually only last 2 turns before the game is over. And here's the really clever thing. If we write out the formulas that differentiate these two structures, right? For the top structure, there is a smallest element, and for the bottom structure, there is no smallest element. If we write out these two formulas, we can read off spoiler's strategy from those formulas. So we see that there exists a point in the top linear ordering such that anywhere duplicator matches it to in the bottom linear ordering, there is going to be some point in the bottom linear ordering such that for any point in the top linear ordering that duplicator matches it to, the ordering is going to be reversed. So directly from the logic, we can read off spoiler's strategy, and directly from spoiler's strategy, we can read off the logic. Let's take a look at another example of an Ehrenfeucht-Fraïssé game. This time the top linear ordering is going to be the rational numbers, and the bottom linear ordering, I've constructed some sort of Cantor set-like thing where I've replaced every single point in the top linear ordering with 2 separate points in the bottom one. And it doesn't really matter how we do this construction. This is a fairly common construction when it comes to linear orderings. You can just imagine we take a point and we split it apart into 2. And again, spoiler is going to want to take advantage of the difference between these 2 structures. So the top structure, the rational numbers, is dense. Between any 2 points, there is another point. For the bottom structure, however, between every 2 groups of 2 points, there's going to be another group of 2 points. But between, for instance, these 2 points, there aren't any other points. So spoiler is going to want to take advantage of that. So spoiler can play here. Duplicator, it doesn't matter where duplicator plays. They're all game theoretically identical. Spoiler plays here. And duplicator now has to pick one of these points. They're also game theoretically identical. And then spoiler can play any of these points up here and end the game in 3 turns, because duplicator has nothing to match this point to. And again, we see that this strategy can be read off of an expression of the difference between these 2 linear orderings. So we see that there is a point x and there is a point y down in the bottom linear ordering that spoiler can play at, so that for any points, x and y up at the top, the duplicator matches it to, there's going to be a z between x and y in the top linear ordering, and there isn't going to be a z. No matter which z duplicator picks in the bottom linear ordering, it's not going to be between x and y. So again, we see this being able to read off the strategy from a formula in first order logic expressing the difference between these two structures. And this is an incredibly tight correspondence. Any formula which distinguishes the two linear orderings, any formula in this very specific logic, which distinguishes the two structures, which is true of one linear ordering but not true of the other, corresponds to a strategy for spoiler to win the game. And what's more, formulas that have n variables in them correspond to strategies that take n turns for spoiler to implement. So by analyzing the strategies that are available to spoiler, not only can we determine whether or not there is a formula to distinguish these two linear orderings, but we can also reason about how big that formula is, how many variables that formula is. This is an incredibly powerful tool, and we can use it to prove logical indistinguishability. So suppose that we're playing the Ehrenfeucht-Fraïssé game between R, with the traditional ordering, and Q, with the traditional ordering. And I'll let you think for a moment, what would happen if we played this Ehrenfeucht-Fraïssé game? Well, it turns out that duplicator can always move, right? There is nothing that spoiler can do because there's no smallest or largest element of either of these linear orderings, and because of density, duplicator can always match whatever point spoiler picks to a point in the other linear ordering. Duplicator is unstoppable, and what this means is that spoiler does not have a strategy for winning in any number of terms. That means that there's no formula that distinguishes these two linear orderings. Of course, they're not isomorphic, they're different sizes. We can't pair up the elements of R and Q together, but there's no way of expressing that difference between these two linear orderings in first order logic. And this is kind of a common theme in model theory, is that first order logic isn't really good at expressing how many of a particular thing there are, right? It can't distinguish between various different infinite sizes. It can distinguish between finite sizes perfectly fine, but between infinite sizes, you need other tools. Specifically, you need tools like isomorphisms, right, where you're talking about matching. And this result gets even more powerful. The same reasoning applies to any dense linear ordering played against Q. In other words, once we know that a linear ordering is dense and doesn't have a largest or smallest element, once we know those three things about a linear ordering, we've determined all of its other logical properties, because those logical properties have to agree with the logical properties of the rational numbers. So these three things form an axiomatization of Q as a linear ordering. All other logical properties follow from these three properties. So we get another interesting result when we analyze finite linear orderings. So if we have two sufficiently large finite linear orderings, then duplicator can last n turns on the game. And you can prove this by induction. It's pretty straightforward to prove. And what this means is that as far as formulas with only n variables in them go, then any two sufficiently large linear orderings look the same. They're going to satisfy the same formulas with n variables in them. And you can also prove by induction that these large linear orderings look like my favorite linear ordering. This linear ordering, omega plus omega star, it just looks like a really large finite linear ordering, but of course it's infinite. And as a result, something kind of subtle happens that allows us to prove that omega plus zeta, so this linear ordering down at the bottom where we have omega followed by a copy of zeta, is logically indistinguishable from omega. If you play the Ehrenfeucht-Fraïssé game between these two linear orderings, duplicator is always going to be doomed. But on duplicator's first turn, they get to decide how long the game lasts. If they wanted the game to last for 100 turns, duplicator could say, I want the game to last for 100 turns, and assuming both players played optimally, the game would last exactly that long. So duplicator can last as long as they want, but on their first turn, they decide how long the game is going to last. They decide when they are doomed. But that's actually enough to show that there's no formula distinguishing these two structures. Because if there was, suppose that there was a formula with 100 variables that distinguished these two structures, then that would mean that Spoiler has a strategy that takes 100 turns, and Spoiler will definitely win following this strategy after 100 turns. Well, all duplicator has to do is say, no, you don't have such a strategy. I can simply declare that the game is going to last 101 turns, and that's going to be whatever strategy you have. So Spoiler cannot possibly have a strategy that lasts 100 turns, and so there's no formula with 100 variables in it that distinguishes these two structures. And this argument works for any value of 100, and so there's no formula of any length that distinguishes these two structures. So I definitely encourage you to play around with Ehrenfeucht-Fraïssé games on your own to try to get a strong intuition for what sorts of games are winnable, what sorts of games are winnable in certain numbers of turns, what sorts of games duplicator can last as long as they want for. It's a really fun and intuitive way of getting an intuition for first order logic. And this is how I got my intuition for model theory. And I use it to this day, maybe not to do proofs, because if you have really complicated structures, actually proving that Spoiler or duplicator has a particular strategy on the Ehrenfeucht-Fraïssé game between these two structures, that's actually kind of gross. But the intuition is still very good and can be used to make guesses that we can then prove in other ways. So thanks for watching. I hope you appreciated these weirdly infinite linear orderings and appreciate how these fairly simple games can allow us to understand this really complicated logical language for describing these linear orderings. And I hope to see you in a future video.